There's only I'm not going to take attendance today, but thank you guys for coming today, and so tomorrow is Thanksgiving, so I just thought I would just express my gratitude and my thankfulness for. Well, there's many things in my life that I'm thankful for, but I am especially thankful for you, my students, and the opportunity I have to teach you guys statistics, and specifically this class 102A, where I get to teach you R and computational statistics, which, as silly as it seems, is something dear to my heart. And so I hope that I hope you guys enjoy the class and maybe are also thankful for it. But anyway, I hope you guys all have a great weekend, great Thanksgiving holiday, whether you go home or you spend it here. I hope you just, at the very least, enjoy some time off and get some sleep and rest, and enjoy the company of others. Today we will we'll take a look at some simulation, and I think maybe one of the because simulation is such a broad topic that I thought maybe we can learn by looking at a case study of a very well done simulation, and this is a simulation written by our friend Hadley Wickham. He wrote a simulation for simulating blackjack, and you know, I don't want to assume too much, but blackjack is a card game that people play in casinos. It's a gambling game, and the goal of the game of blackjack is to have the total of your cards. So everybody starts off by being dealt 2 cards. Every single card in the deck has a point value, and the goal is to get your total point value as close to 21, or to 21, or as close to 21 as possible without going over. If you go over 21, you lose the game immediately. And one of the unique things about blackjack versus other games in the casino is that they do not shuffle the deck after every hand that is played. Okay, and so many people have taken advantage of this via what they call card counting to get some idea of what cards remain in the deck. Okay, so you know, clearly if we were playing with only one deck, there would be 52 cards, and if you keep track of the cards that have been dealt, you can have an idea of what cards remain in the deck. Now, most modern casinos don't play with just a single deck. They will play with what's called a shoe, which is generally a stack of maybe 4 to 6 to 8 decks of cards. Okay, and this is mostly to reduce the need to constantly reshuffle the decks. So you might have 6 decks stacked together, so 6 times 52 would be 312 cards. You have 312 cards, and you know, card counters would keep track of which cards have been played. They would have an idea of what cards remain in the deck, and if they believe that the cards that remain in the deck are towards their favor, they would increase their bet. Now, card counting is not illegal as long as it is done unassisted. Okay, it is illegal to use a computer to assist your or any kind of device to assist in your card counting. Card counting is not illegal. It is discouraged, and if they catch you card counting, or if they suspect you're card counting, they might ask you to stop playing blackjack. But there's been a lot of theories and systems developed to count cards, and then there's this question of, does card counting actually help people quote unquote beat the house? Meaning, if we keep track of the cards and get an idea of what cards remain in the deck, can we bet so that our expected winnings are actually positive? Okay, most games in the casino that are purely chance-based, such as craps where you roll the dice, roulette where you spin the wheel, other games generally are designed so that the casino, the house, maintains an edge in all the gameplay. But as far as blackjack goes, if you are successful at card counting, there is you can actually turn the expected win rate to be something positive versus generally negative. Okay, and so the simulation here will explore kind of the effects of card counting on this, right? So this would be a difficult question to answer just from a pure analytic perspective. If we said we're going to implement this card counting system, you know, how does it affect our win rate? That's really hard to answer analytically, and so we can build a simulation to simulate the process of playing blackjack and see how effective we can be at maybe turning a profit in the game. Okay, so just some basic rules about blackjack. So in the deck of cards, there are 52 cards, but only the value of the card matters. So whether it is what suit, clubs, hearts, spades, or diamonds, that does not matter. It's just the value. Okay, and so the values of the cards, the ace is well, the spot cards, basically 2 through 10, are worth their face value. All the face cards, Jack, Queen, and King, are also worth 10, and the ace is worth 1 or 11, depending on whichever is more favorable for you. Okay, and so we can create a deck by taking 1 through 10. This represents ace through 10, and then Jack, Queen, King, and this would be kind of the 13 different values that exist in the deck, and we would multiply that by 4. The general wisdom for card counting in blackjack is that the 10s and the ace are good cards, and the 2 through 7 are like bad cards or unfavorable cards, and then the others, the 8 and the 7, 8, and 9, those are kind of neutral cards. And the idea being, if you get dealt two 10s, you know, your hand is worth 20, which is generally seen as a favorable position. Okay, and so that's what we do. If we look up blackjack on Wikipedia, the Wikipedia entry on blackjack contains there's a lot written about how to play blackjack. It contains kind of the optimal strategy. So the things that you can do when you are playing blackjack is these are kind of your decisions. Is first you are dealt 2 cards, okay? So maybe you're dealt a 3 and you're dealt an 8, okay? At that point, your cards are worth 11 points. 3 plus 8 is 11. And then you're given a choice. You can hit, which means you accept another card from the dealer, or you can stand, which means you are going to keep the 2 cards that you have, or keep however many cards you have, and say, this is the point value that I will submit to play against the dealer. Those are your 2 basic turns, but you can also double down, which allows you to increase your bet and accept 1 more card. Or you can split, which means if you have a pair dealt to you, let's say you are dealt 2 8s. If you're dealt 2 8s, you have 16 points total, which is considered not a good total. You can split those, and you would have 2 hands now with 8 points, and you would take another card to each. Surrender, we'll ignore the surrender here. Okay, there's other stuff, and then generally the dealer is continued. The dealer has no choice in how to play their cards. The dealer must continue to hit their hand until they reach 17 or higher. So if the dealer is at 16, the dealer has to take one more card. If the dealer is at 17, the dealer must stand. Okay? And so the Wikipedia page contains kind of the optimal strategy of saying, you know, what you should do. Okay, so if you are dealt 12 and you know, you would hit or stand or whatever it might be. Okay, so you're dealt 2 cards, the dealer's dealt 2 cards, but one of the cards of the dealer's is showing. Okay, and this gives you some insight as to what total the dealer may have. So depending on the one card that you see of the dealer and your card total, there's this table of what you should do. So if you have a 17 through 20, you should stand. You shouldn't accept more cards. If you have a 16 and the dealer shows a 6 or less, you should stand. However, if the dealer shows 7 or higher, you should hit. Okay, or in some cases you should surrender. But we're going to ignore the surrender and we'll say you'll hit. That's kind of the basic strategy. But then they have other things such as you should split or things like that. There's what we call hard totals and soft totals. Okay. This refers to the fact that the ace can be a 1 or an 11. So if you have an ace 5, an ace 5 is worth 16 points, but it's considered a soft 16 because if you are dealt, let's say, an 8, okay, an 8 after that, normally 16 plus 8 would be 24 and you would lose, but because the ace can change values between 1 and 11, if you have a 1-5, or an ace 5, that's 16 plus 8 becomes 24, your ace changes to a 1 rather than 11. So now you have a 1, a 5, and an 8, and now you are at 14 points, okay? So you don't bust if you have a soft total, okay? So a soft total means that your ace is currently 11 and can convert down to a 1 if need be, okay? And so this references kind of maybe some strategies that can be employed. That's a very brief introduction to the game of blackjack. I don't know if we have any questions regarding that before we get into setting up the simulation in R. We're okay? All right. Well, okay. So basically, I'm going to just follow along. And you know, if you have the time, I do encourage reading through what Hadley wrote in terms of his simulation of blackjack. It would take more than the 50 minutes that we have in class to go through the entire thing, so I'll just kind of give a highlight tour. And this is actually an excerpt from the Data Science with R case studies book, which I can link, and I would recommend checking that out as well. Okay, so we're first going to start with a simple simulation where we set up the deck as 52 cards, and what we will do is we will initially draw cards using a kind of with replacement. Okay, so we aren't keeping track of which cards have been drawn. Later on, we will implement the idea of a shoe. Here we have a function to calculate the value of our hand based on the cards, a vector of cards that we have. Okay, so in this case, our hand value calculation just says take the cards that you have and sum them up, and then we apply any of the special rules. If any of the cards is an ace, and the total value is currently right now is 11 or less, we can take that ace and make it worth an additional 10 points, and that would be our value. Okay. However, if our value goes over 21, which means we have bust, the value of our hand will be worth 0. And on the other hand, if you are dealt an ace-10, okay, which is considered blackjack. An ace-10 is worth 21 points, but if you get blackjack, that beats getting 21 via 3 or more cards. Okay, so 3, 8, and 10, although adds up to 21, will lose to an ace-10. Okay, so ace-10 gets special treatment as blackjack, and that one will beat getting 21 via the thing. So via blackjack. Okay, and so and in fact, casinos will pay out 1.5 if you get blackjack. Otherwise, all other bets are generally paid even money. So so if you bet 10 and you win the traditional way, you would get $10 from the casino. However, if you bet 10 and you get blackjack, you would get 15. Okay. The only time, so if you get blackjack, it's almost an immediate win. The only time you would not get an immediate win is if the dealer also is dealt blackjack at the same time. Then it's a tie and nobody wins or takes money. Okay, that's called a push. Okay, and if the dealer is dealt blackjack, then the dealer also wins immediately, kind of type of thing. Okay, and so we have all sorts of rules for winnings. What we do is we'll look at our hand value versus the dealer's hand value versus our hand value. If the dealer has blackjack, then we lose. Okay, which will be our winnings will be -1, as long as we also do not have blackjack. Okay, so if the dealer has blackjack and we have blackjack, then this would this thing would be 0, right? So if the dealer has blackjack and our hand is also a blackjack, then this would be 0 and our winnings would be 0. Otherwise, our winnings would be -1. Okay. If the dealer busts, then we win 1.5 for our blackjack. We win 1 for anything that we have. However, if we bust, we lose. Okay. So if we go over 21, we lose immediately, whether or not the dealer has bust or not. Okay. So if I bust, if the player bust and the dealer bust, then we still lose. It's not considered a tie there. Okay. And then lastly, if then we just compare. If we are over 21, then we win 1.5. If we are as long as we're greater than the dealer, we win, and if we are less than the dealer, we lose. Okay, so this will return either -1, 1.5, 1, or -1, or 0. It returns 0 if basically all of these things end up being false, right? So if the player and the dealer tie, pretty much all of these statements would equal 0, and so the winnings returned would be 0 as well. So that's so what we've done is we've set up functions to kind of calculate values that we need, the hand value and the winnings, and that's what we have. This is kind of a shorthand version of formulating the winnings, and here is Hadley is very big into having systematic testing to make sure that the functions you've written perform in a way that you expect. And so here he's created a list of test cases, such as if we do 10-1, which would be a 10 ace, that should be worth 21.5. And you know, all of these different things are just different hands that have been dealt, and we're asking, does the hand value function calculate hands correctly? Okay, and so here we're going to just run through these. Here we list off exactly how much each of these hands should be worth, and to make sure that our hand value is working correctly, we're going to apply to this list the hand values function, and we will check to make sure that the output of this is identical to the output, what we're expecting here. Okay. So indeed, that's what we have. But you know, we could if we could just make sure do this one at a time and just see if the hand values return exactly what we expect. So if I'm dealt a 5, 6, and a 10, that should be worth 21, and running hand value does indeed confirm that. Okay, so this is just a way to kind of automate all of this, or not automate, but just run through in one statement. But we could also just check it manually, one vector at a time. Yes.
There are 221, one of them with 10, 5, and 6, the
Yeah.
other one with 3, 6, 1, 1. In this case, who would win? Because the 21 on top has less cards.
They're worth equal. Okay, they're equal. So 3, 6, 1, 1 is worth 21, and 10, 5, 6 is worth 21. They are equal. They would tie in the game, and if you and the dealer tie, then it's known as a push, and basically the money that you put down on the table as a bet just gets returned to you. You don't take any of the casino's money. The casino doesn't take your money. It just says, okay, you bet $10, you get to take that $10 back. Okay. If you lose, the $10 you bet, it now belongs to the casino. If you win, the $10 you bet returns to you, plus the casino will give you $10. Okay.
The only one that outranks is the 10 and the 8.
Yeah, an ace-10 is a blackjack, and that beats every other hand, but it ties another blackjack. Okay, so if you have an ace-10, that's worth 21, but it will beat any other hand. So in our system, we call that 21 and a half. Okay, just to kind of make sure that it wins all other things. But if you are dealt blackjack and the dealer's dealt blackjack, then again, it's a tie, it's a push, and whatever you bet just goes back to you. Okay, so this is just a way to do to check. Okay, here we are creating a matrix to make sure how to see if the winnings will compute out correctly. So this is the case where the player busts, the player has 16 versus 19, 20, 21, or blackjack. Okay, and we're gonna just say, all right, if the player, let me just show you what this thing looks like. Test winnings. This is a matrix that says okay. So if the player busts, depending on then our winnings versus any of these dealer hands would be -1. Okay, and on the other hand, if the player has 20, then the player wins money in all of these cases. The player, if the dealer has 20, there's a tie, and if the dealer has any of these things, the player would lose money in this case. And if the player has blackjack, then the player beats everything except against the dealer where there's a tie. Okay, and so this is kind of the matrix that we would expect to happen if the player plays against the dealer. Okay, and we can just we can go through and we will create a blank matrix called check. Okay, and so the check matrix is the same thing except it's all blank. And what we're going to do is we're going to run through and just see, okay, if winnings does our winnings function return the values that we expect? So we go through each cell in the matrix and we just say, let's plug in 0 and 0 into the winnings function to make sure we get back what we expect. All right. So this the test winnings matrix represents what we expect. And then we will run through this loop, which goes through every cell. And we're going to just see, okay, after we've done that, let's see what the our check matrix looks like. This is what it looks like after we've populated it with every single test case. And then we will just do, is that identical to what we expected? And it says, indeed it is. Okay, so here we've just, all this was to do was to just test the functions and make sure that they are working properly. Okay, so they seem to be working properly. Here, our shoe function will just be a call to deal out a new card. In the beginning, we just use sample with replacement. Later on, we will implement a reference class to keep track of the cards that we've played. Okay, and we have functions to create a new hand using object S3 object-oriented programming here, so that we have something of the class hand. Okay, so if I just call new hand, okay, whoops. Okay, so here the hand object is a list that contains my bet. The actual function for drawing new cards is contained within the object for hand, along with the cards that we have and what class that we have. Okay. Well, to make our lives better, we will create a custom print function, print.hand, which will just make the output a little bit better here. Okay, which will paste the cards that we have along with the bet and output the hand value of our cards. So now if I call my cards, rather than printing out the list in its traditional nature, it will say this is a blackjack hand. These are the cards that have been dealt, which is worth 7 points, and my bet right now is $7. Okay, and we will implement some functions for the actions that we can take. Okay, so as far as hit goes, it's a function of the hand itself, and because the hand object contains the method for drawing additional cards, we can do that. So we can the hit function will say update the cards in your hand by combining the current cards with a draw from the shoe. Okay, and then after you do that, return the hand itself. So I will run the hit. Okay, so if we take a look at my current set of my cards, I've got a 4, 3, and a 7, and if I hit, then I have 4, 3, 10. So it returns the hand along with the cards. Okay, and again, if I did print.default on my cards, we can see that it contains. Oh, I didn't actually capture the output there, so I would need to do hit my cards and store that as my cards. Okay, so maybe. So I got dealt a different card this time, and that's what we have. Okay. On the other hand, the stand function, which seems a little silly to have right now, it's just going to return your hand. Okay, so we will do that. Okay, doubling down will increase our bet and do a hit, and then we stand. Okay, so that's what we have. Doubling down will do that. Okay, and then splitting a pair, it feels a little bit crazy. And what that will do is it's going to return 2 hands. Okay, so the function split pair will return a list of 2 hands, such that the first one will be a new hand made out of the first card in my current hand, and the second will be a new hand made consisting of the second card in our current hand. Okay, so this is all done here, and we do that. So let me just create. We'll create a new hand, and we can do the split hand. And here, well, we got lucky. We started off with 10, 10, and then we got dealt 10s each. And so we have two hands of worth 20. So that is you know, that was lucky here. Okay, so here if we deal ourselves some cards, we can just kind of simulate, maybe not simulate, but just see, you know, we could say, like, let's take a look at what the dealer has. The dealer has a 5. Our hand, we have 15. So what we would do is we would hit, okay, and we got an ace, so we'll stop at 16. The dealer has 10, the dealer will hit, and the dealer has 20. And so if we compare our hand versus the dealer's hand versus our hand, we have lost. Okay. We can create a function for the dealer cards, okay? And it basically just says, you know, keep hitting until the dealer's at 17 or more. Okay, so just while hand cards are under 17 and we haven't bust, keep hitting the cards is what we have. Okay, and then we will implement a very simple strategy in the beginning, which is as long as if I bust, then I've got to stop. However, if the dealer shows 7 or higher, and we are under 17, we will hit. Otherwise, we will stay. Okay, which is kind of your basic. If you don't know anything about blackjack, that's the kind of the one rule, which is if the dealer shows anything under 16 or under, you should stand. But if the dealer, you should only hit if the dealer has something, shows a 7 or higher, and you yourself are under 17, okay? That's the only time you should hit. If the dealer shows 7 or higher, and you yourself have under 17, then you hit. Otherwise, just stand, okay? That's the most basic strategy, which is kind of what we have here, okay? Stand for everything here, and then if the only time you hit is if your hands are 16 or lower, and the dealer shows 7 or higher. Okay, so basically it's just we're pretending everything is red and over here is green. Okay, that's your basic strategy. Otherwise, you stay. Okay, so so that's what we have. We'll skip this prompt user thing. Okay, and so the function play hand takes into is a function of how we're going to draw cards, the strategy we're going to use, and then it creates a hand for ourselves and a hand for the dealer. Okay. And so if we do if we click play hand, it just went by very quickly, and it just says, all it does is it just returns the winnings, whether we won or lost, okay? And so here we're kind of on a lucky streak. We won, we got blackjack the first time, and then we won, and then we lost. And so all this is doing is it's just kind of shortcutting everything and just telling you whether you won or not. Because ideally, what we want to do is just see how often we win or how often we lose. We can modify this because right now this is very opaque and we can't really see what it's doing. So we can modify this by adding a verbose option to print out exactly what it's doing. Okay, and so we'll just start off with our initial thing, and then we do verbose is true, and this tells us what the dealer did. It was started off with 5-5, and then it dealt itself a 6, so it had 16. So by the rules of the blackjack, it had to take another hit, and then it bust. So its total hand is worth 0. We got dealt a 10-1, an ace 10, so we stand and our hand is worth 21 and a half. Okay, so we won there. If we click play hand again, we could see the other time. So the dealer had a 10-3, 13. It took a hit and it lost. Okay, it bust. We had a 2-7, which was a 9, and then we took a 10 for 19, and we won, and so on and so forth. Okay, so here the dealer again 2-4, 8, 14, took a hit, it bust. We had an 8-4, which is worth 12. We stand and we win. Okay, and then here's one. The dealer had 18. We played 3-10. Okay, we saw the dealer's 8, so we took a hit. We went to 23. We bust and we lost. Okay, so this is so that's with verbose, but what we can do is we can just implement you know, with the verbose set to false, and then all we will do is, oops, verbose is true. Okay, so you know, we can just replicate this with verbose equal set to false. Okay, and if I just did replicate this, I don't know, 10 times. Wait. How does replicate work? Do I do it this way? Okay, so this tells you kind of what happened, and so we can see that the how often or how little we lose just implementing our simple strategy. Okay. Instead of using the simple strategy, we can use the lookup table. I guess I have to upload that to CCLE, which basically implements this optimal strategy that we've taken from Wikipedia to do this. Okay, and so if we look at the optimal strategy, it tells us whether to stand or to hit based on what we have, and we can implement this as a function. And I'm going to just kind of skip through all of this, and this is kind of just the test to make sure that it's working properly, and here we will just see how often we win or lose using the optimal strategy, okay, versus the simple strategy. And we can do 1,000 replications of this between the simple and the optimal strategies. And here is a plot that we have of this. Okay, and so just a comparison of the simple strategy versus the optimal strategy. Okay, purple being the simple. So when you have the simple strategy, which is either just hit or stand, we can see we have a peak at 1, a peak at -1, and a little peak at 0, which is kind of how often we win or lose. The optimal strategy also has a little peak at -2 and a little peak at 2, which indicate that we can also double down, so our return can be 2 or -2 and things like that. Okay, and so if we implement our optimal versus our simple strategy, the mean of our optimal strategy is -0.03, so we lose about 3 cents on the dollar on average, and if we use the simple strategy, we're losing about 5 to 6 cents on the dollar. Okay, and the payoff is, let's say, rather than, so that's if you play 1,000 games. Here, payoff is going to be, what if I decide to go to the casino and I play 50 games and I make 1,000 trips to the casino? We can do this and all of this, and this is what we get. And we'll create a plot of this. So this is 1,000 trips to the casino, each trip being 50 games, and we can kind of just see the optimal versus the simple strategy. This is kind of, if you played 50 games using the optimal versus the simple strategy, what was the winnings for that trip to the casino? And we see with the optimal strategy, we get slightly better performance than with the simple strategy, where the center is a little bit negative, and with the optimal, maybe it's less so. Okay, but you know, that's just one picture there. Okay, this is all just code that Hadley uses to explain how kind of some reference classes go. And so now we're finally going to implement a reference class for drawing cards, which will allow us to keep track of the cards that we have drawn for the purposes of counting cards. Okay, so the shoe now is going to be a reference class where we keep track of all of the cards that we have. It includes a few methods for shuffling the entire shoe and drawing cards from the shoe, and it will also keep track of, you know, which cards that we have played. Okay, So in the interest of time, I'm not going to go through all of the details of this function here, but you can review this yourself. And so what we can do is, if I can create a new shoe called my shoe, and this lists off all of the cards that exist in our shoe. So here our shoe consists of 3 decks, and this is the current order that we have. And what we do is we start off at position 0, and as we play cards, we increment our position, and we can see, we can learn what cards will be drawn next, okay? And so this allows us to keep track of the cards that will be played, okay? I've based the manual dice function in the Monopoly code off of this manual, this shoe reference class thing. So there are similarities here in that we are given a vector of values, and we keep track of the position from which we've played. Okay, and we can just see what happens if we draw cards, and how it updates our position, and how many decks that we have left, and so on and so forth. Okay, and when you draw more cards, it will tell you to shuffle the shoe, and so on and so forth. Okay, so here we'll build up a shoe with 6 decks, and we can use this to play cards from the shoe. And so if I list off my shoe, and we take a look at the cards that have been played, we can see that when we look at the cards that have been played, which were a 1, 8, then a 4, a 10, a 1, and a 10, we can see exactly where they're coming from. Here's the 1, 8, here's the 4, the 10, the 1, and the 10. Okay, so the cards that we are using to play, when we call the reference class shoe that we have drawn, we can see exactly where those cards are coming from. And this allows us to just ensure that the cards that are being drawn are not coming from simple random sampling, but instead from a shuffled deck where we are dealing them out. This is then useful to us because what we will now implement is some card counting strategy. Okay, and so the way we will do card counting, which is we're going to use the high-low card counting system, which is basically if a good card, being the ace or a 10, is played, that decreases the card count, okay? Because if good cards are played, that means there's fewer good cards left in the deck, and therefore what's left in the deck is less favorable towards you. On the other hand, if a bad card is played, a 2, 3, 4, 5, or 6 are played, that increases what's the probability of getting something good in the future. So that increases the count, okay? And then a 7, 8, or 9 are considered neutral, so that will neither increase nor decrease the count. And this is how we do it. We're using subsetting, basically duplicate subsetting here to do that. And the card count is also going to be depends on how many decks have remain. Okay, and so this is our card counting system, and so we can see we can apply this to if I do my shoe $played. Whoops. These are the cards that have been played, and I can apply my count function to this to see, what is the count of cards, okay? And so here, because, several 10s and a few aces have been played, and, if we keep track of this, currently the count of the cards left in the deck is -1. But we would, so we would use this, the count of the cards, to increment our bet. So our bet will be based on the count, and here we can just plot and see how as the card count increases, our bets will also increase. Okay. So all this goes into trying to calculate what our payoff would be. So the only thing that the card count affects is how much we bet. The strategy of whether to hit or to stay remains the same, but now what's changing is, do we bet the minimum or do we increment our bet? And so we will play, apply this to 1,000 games, or 1,000 visits to the casino where we play 50 games at each time. And we can get an idea of how this compares. Okay. So here we actually, I guess, got lucky in this scenario. This is our payoffs between standard, keeping the same bet, versus increasing our count, increasing the bet based on the count. And we can see that if we increase our bet based on the count, we do come out ahead in each thing, but also the standard deviation of our winnings come out much greater. Okay, so on average, this is what we have, and so here, let's just. So this is kind of a plot showing the difference. So a lot of times, using the card counting system versus the fixed bet, most of the time our difference in gains is 0. Sometimes card counting puts us behind, but if we look at kind of the right tail, there's a little bit more on the positive side, and so this is a little bit of simulated evidence that indeed card counting can put us ahead in the long run. Okay, this was, I know we worked through this very, very, very quickly, and maybe we didn't catch all of this, but again, if you have the time, I recommend reading through kind of this chapter article that Hadley Wickham has written, and it's very sound in just kind of explaining every single part of the simulation that he has written, and it allows us, again, to gain some insight into building up a simulation, to ask and answer questions regarding something related to probability that would be much too difficult to answer in just a purely analytic fashion. Okay, we'll end here, and again, have a wonderful Thanksgiving weekend, and we will see you guys on Monday. So.